Bismillah ar-Rahman ar-Rahim. Today we have very interesting talk about convergence of series. Now, if you remember so far, what we did is this. We have an infinite series. We have n equal to 1 up to infinity, and we have an here. And we need to investigate whether the series is convergent or not convergent. So we defined first what is the meaning of convergence of series. So we said we need to define what we call the sequence of partial sum, okay? N equal to 1 up to infinity, and then we said if the limit as n goes to infinity of Sn is equal to S is a real number here, real and finite, then we said that the series is convergent. Then we passed through some famous type of series like the geometric series, like the telescoping series. Then we introduced some tests for convergence like the integral test, like for example the comparison test, limit comparison test, alternating series test. Today we will add another kind of convergence, that's one thing. Then we need to see the relationship between the two types or three types of convergence. And finally we need to add two other tests. One of them is called the ratio test and the root test. So today we'll talk about absolute convergence, that is another type of convergence. And we will add the ratio and the root test to investigate convergence of series. So what does it mean first? Absolute convergence. The definition says a given series, an infinite series, n equal to 1 up to infinity, an is said to be absolutely convergent if the series of absolute values, after taking absolute values of each term here, term-wise, then we end up with a series of absolute values. If this series is convergent, the original series is said to be absolutely convergent. So let us take an example to understand this terminology. Now a question here says, example says, show that the given series here, which is given by summation n equal to 1 up to infinity, and that is minus 1 to the power n minus 1 divided by n squared. It said show that this is absolutely convergent. Show that it is absolutely convergent. So what do we need to do if we need to prove that a given series is absolutely convergent? The only thing we need to do is take the series, take the absolute value, and prove that the new series obtained is convergent. That's exactly what we need to do. So I will consider now this series, which is the series with absolute values, n equal to 1 up to infinity. I will take absolute value of the nth term there, minus 1 to the n minus 1, all over n squared, okay? And clearly this will give me what? This will give me the series n equal to 1 up to infinity. Of course, the minus sign with the absolute value will be gone, so this will be 1 over what? 1 over n squared. Now, what can we say about the new series obtained here? The new series is one of the famous series we treated before by the integral test. This is called a P series with P equal to 2, which is greater than 1. So this new series is convergent. Because this new series is convergent, the original series is convergent, absolutely or absolutely convergent. Let us write this summary here. It says now, this is a B series, this new series, this series is a convergent P series. It is a P series with P is equal to 2, which is greater than 1. So it is convergent P series. So the original series now, the original series we have, which is summation n equal to 1 up to infinity, that is minus 1 to the n minus 1 divided by n squared is, let us say, is absolutely convergent. So in order to prove a given series is absolutely convergent, we need to prove that the series with absolute value is convergent, and it is in this case convergent, so the original one is absolutely convergent. Okay, so do we have a convergent series which is not absolutely convergent? Okay, let us see the second example and study this, make this discussion about the following series. Okay, the second example here says, is the following series, is the given series, which is the series given by this summation, which is n equal to 1 up to infinity minus 1 to the n minus 1 all over n. Is it absolutely convergent? Then I ask another question, is it convergent? Is it convergent or not? Is it absolutely convergent? Is it convergent? That's what we need to answer. Okay, if we need to answer the first question, what you need to do is to take the series with absolute value. Okay? So we consider this series now. The series with absolute value, so this is the summation here, n equal to 1 up to infinity, and then I take the absolute value of minus 1 to the n minus 1 divided by n, and clearly this will give me summation of n equal to 1 up to infinity of 1 over n. Now, this is very famous series called the harmonic series, you like, or you can call it, it is a p series with p equal to 1. And both will give you the same conclusion that the series is divergent. Which is divergent? Yeah, why it is divergent? This is the harmonic series. So one of the famous examples we did before, the harmonic series, it is convergent, or you can say it is a p series with p equal to 1. So what can we say about the series? Is it absolutely convergent? The answer is no. In order to be absolutely convergent, we need the series with absolute value to be convergent. So the question now, or the answer for our question is, the series is not absolutely convergent. Okay, so that's what we have. Now, if it is not absolutely convergent, is it convergent? Is the series convergent? Now look for the series. Look for this series given here. You see it is very also famous one. It is the alternating series we treated by alternating series test. This is alternating series. This series is convergent. Why it's convergent? Okay, note that this is what we have. The series given here, the series given by this summation n equal to 1 up to infinity minus 1 to the n minus 1 all over n is convergent by alternating series test. Okay? It is convergent by alternating series test. Why it is convergent by alternating series test? This is what we did before. We have our Bn, this is alternating first, it is alternating series. We have Bn is equal to 1 over n, and we have the two conditions, if you remember. We have Bn plus 1, which is equal to 1 over n plus 1, that is less than 1 over n, which is equal to Bn. So, and this is true for all n, for n greater than equal to 1. For all n greater than equal to 1, we have Bn plus 1, this than Pn. The second condition we have, the limit as n goes to infinity of Bn, it's equal to the limit as n goes to infinity of 1 over n, and that's equal to 0. By these two conditions we have, the alternating series test says this series is convergent. So, you can see now we have an example where the series is convergent. You can prove this is convergent by alternating series test. After taking absolute value, still it is convergent, so we call it absolutely convergent. For the second one, the series is convergent. But once you take absolute value, you end up with a divergent series. So this series is not convergent absolutely. It's only convergent. Now, the question is, the first question is, what is the relationship? Which one implies the other one? If the series is convergent, is it absolutely convergent? Of course, the answer is no, because of this example. If the series is absolutely convergent, is it convergent? That's a question need to be answered. That's one thing. The second one, if a series is convergent, but when we take absolute value, it is not convergent. It is not convergent absolutely. What do you call it? And that will be our next definition and next theorem. So the definition says now, another type of convergence, if a series is convergent, but not absolutely convergent, then it's called conditionally convergent. It is conditionally convergent. An example of this, we just discussed this example that says this series is convergent by alternating series test. Once we take the absolute values, it became 1 over n, and 1 over n is divergence. So this series is called conditionally convergent. The question now, which type of convergence implies the other one? For example, the theorem here says, we have a nice theorem that says, if a series AN is absolutely convergent, then it is convergent. We know that if a series is convergent, it is not necessarily absolutely convergent. So the converse is not true, not always true. If a series is convergent, it doesn't mean that it is absolutely convergent. This theorem says no. The other way around, if it is absolutely convergent, then for sure the series is convergent. That's one thing. Okay, I will prove this one for you, but let's discuss also the relationship between conditionally convergent and absolutely convergent. Okay, you may have a series that is convergent conditionally. If it is convergent conditionally, for sure it is not absolutely convergent. You cannot have a series which is absolutely convergent and conditionally convergent. Cannot be. Because in order to be conditionally convergent, it's supposed to be absolutely divergent. I mean, if you take absolute value, the series will be divergent. But for this nice theorem, we have a relationship now that says, if a series is absolutely convergent, then it is convergent. How to prove this? Just an idea of the proof. What is given here? We are given that this series, we have n equal to 1 up to infinity with absolute values. This is convergent. This is what we have. That is what it means, absolutely convergent. So this is given. Once you take absolute value, the series is convergent. That is what is given. Now, I just give you this note that any real number, an, any real number, is greater than or equal to, less than equal to, it's less than equal to its absolute value, and it's greater than minus its absolute value. This is always true for any real number. Okay? Now, if we add just the absolute value of an to all sides of this inequality, this will be 0 less than equal to an plus absolute value of an. And that is less than equal to twice absolute value of an. Now, the question is this. We have non-negative terms. Okay? So we have non-negative terms. What can we say about the series summation of n equal to 0, okay, n equal to 1 according to our setup here, n equal to 1 up to infinity, 2 times an. Okay, this is convergent. Why it is convergent? Because it is constant multiple of a convergent series. This is equal to 2 times summation n equal to 1 up to infinity absolute value of an. Now, by the given we have, this is convergent. Multiplying a convergent series by constant multiple, that is still convergent. So we can say now, this series is convergent. Since this is convergent, what is the conclusion? Then we have the following. See, we have a series which is given by 2 absolute value of an. This is convergent. So by comparison test, the series here is also what? Convergent. So this implies that this series now n equal to 1 up to infinity. This is an plus absolute value of an. This one also is convergent. So now we gain something beautiful here. We started with this series is convergent. We end up with this series now. This series is convergent. Fine. What's our target? Our target to show that this series is convergent. This series is convergent, but it's clear that what is this series an? n equal to 1 up to infinity, I just write here an. I need to show that this is convergent, and that is not difficult. I will write it down as this is summation of what is an. You can say this is n equal to 1 up to infinity. You can write like this: an plus absolute value of an minus absolute value of an. This is exactly equal to an, isn't it? So this is an minus plus absolute value cancel each other. Now, look for this series with these two terms. Look for this series by itself, okay? The series with an plus absolute value of an is convergent. We proved this. And the series with absolute value is convergent. That is given. So what can you say about the difference of the two series? Also is convergent. That is one theorem we did at the beginning of discussion of series. So this is equal to. Now we can distribute the summation because this is convergent and this is convergent. So we can distribute, and this will be what? Summation of n equal to 1 up to infinity an plus absolute value of an minus summation of n equal to 1 up to infinity, and this is absolute value of an. Now, this is convergent series, this is convergent series, so the difference is convergent, but the difference is exactly an, so an is convergent. So being a difference of two convergent series, put it like this, an is convergent. What is the conclusion now? The conclusion is, if you have absolutely convergent series, then for sure it is convergent. If you have a convergent series, it is not enough to say it is absolutely convergent. If you have absolutely convergent, then it is not conditionally convergent. If it is conditionally convergent, it is not absolutely convergent. That is the summary of the type of convergence we have and the relationship between them. Now, let us see an exercise about, another exercise about absolutely convergence and how it will help to solve or to add more exercises about series now. If you remember, many tests we did have a condition that the term should be non-negative. Okay? The integral test, we have the term should be non-negative. Comparison test, the terms should be non-negative. The limit comparison test, same thing. We need non-negative terms and etc. Now, this nice relationship between absolute convergence and convergence will add more freedom to solve different type of exercises. So let us discuss one exercise here about absolute convergence that says, example, it says determine whether the series here, this series is given by this summation n equal to 1 up to infinity. Now we have cosine n divided by n squared. Okay? Whether this series is convergent or divergent. Okay? That's the question. Now, what is the contribution of absolutely convergence here? Look, if we try to apply the previous test we have, we cannot, because cosine n, it's sometimes positive, sometimes negative. So we cannot apply the comparison test directly. A common mistake here, maybe someone would say, okay, we have cosine n all over n squared is less than or equal to 1 over n squared. And since the series of this is a p series with p equal to 2, which is convergent, so this is convergent. We cannot do this directly. Why? Because we are not sure that all or both of these will be greater than or equal to 0. That is a very important requirement in the comparison test. So we cannot gain the conclusion from comparison test. So what should we do then? What should we do? Simply, we need to take absolute value. So, in order to see this, I will take the absolute value of cosine n over n squared, and I know that this is less than or equal to 1 over n squared, but at the same time, I know that this is greater than or equal to 0. So, after taking absolute value, now we can use comparison test. Now, comparison test says, since what? The summation of n equal to 1 up to infinity, this is 1 over n squared. since this one is convergent, now why it is convergent? This is something we did before. It is justification. P series, you're supposed to know this. P series with what? P equal to 2, which is greater than 1. And that's the criteria for the P series test. If P greater than 1, it's convergent. Less than or equal to 1, it is divergent. Okay. So, since this is a convergent P series, let us say like this, then what is the conclusion? Then this series n equal to 1 up to infinity, absolute value of cosine n over n squared is convergent. By what? This is convergent by, let us say, comparison test. Okay? So what is the conclusion? Look, we started with the question here. We take the absolute value. We end up with another series. This series is convergent. So the conclusion that this series with absolute value is convergent. So what can we say about the series without absolute value? Without absolute value, it will be what? Convergent absolutely. Why it's convergent absolutely? Because after taking absolute value, it is convergent. So it is convergent absolutely. And if it is convergent absolutely, what can you say about the series? It is convergent. So the conclusion now, this implies this series n equal to 1 up to infinity, cosine n over n squared is what? Absolutely convergent. Okay? So I don't need to write also, since it is absolutely convergent, this will be understood. Once you write absolutely convergent, by default it is convergent as a result of this nice theorem we have. So that is basically what do we mean by absolutely convergence, conditional convergence, etc. We'll take another example to have more examples about these terminologies: convergence, absolutely convergence, conditionally convergence. So let us discuss more examples about these definitions. Okay, we have a nice exercise here that will also help us to understand more about these things. So the question here, the exercise says, again determine whether the given series, the series is given by this. N equal to 1 up to infinity, and that is minus 1 to the power n e to the power 1 over n all over n cubed. Okay? Determine whether this series is absolutely convergent, conditionally convergence, or divergent. Okay? If it is absolutely convergence, for sure it is convergent. If it is not absolutely convergent, it may be conditionally convergent. If not, then it is divergent. So what should we do to solve the exercise here? Again and again, don't forget that we cannot apply the integral test or the comparison test or the limit comparison test. Okay, we may apply the alternating series test to check the convergence here. But for me, I advise you to start always with the absolute convergence. If it happens to be absolutely convergent, you are done. It is convergent. If it is not absolutely convergent, then you need to check convergence by another test, maybe the alternating series test. If it is, then it is called conditionally convergent. If not, then it is divergent. So, let us take the absolute value here. Absolute value of minus 1 to the n e to the power 1 over n all over n cubed. This is less than or equal to what? Of course, when you take the absolute value, the minus sign will disappear and we have e to the power 1 over n cubed. And you can show that this is less than or equal to e over n cubed. Why is this? Why this is the case? why this is less than or equal to E all the time for n greater than equal to 1. For n greater than equal to 1, we can prove that this is always less than E. Why this is the case? I will show you this. Before I move to find the solution of the series, let us say some words about the equality here. Why this is true. Okay, so we know that this is also greater than equal to 0 all the time. I will just say something about this. If I need to prove that if f of x equal to e to the power 1 over x, then this is always less than equal to e. That's what I need to show. The maximum here is equal to e for x greater than or equal to 1. Just use the derivative, f prime of x. What is f prime of x? This will be minus 1 over x squared, e to the power 1 over x. This is always positive, and this is always negative for x greater than equal to 1. Okay, since always negative for x greater than equal to 1, it means the function itself is always decreasing from 1 to infinity. So if you have a decreasing function from 1 to infinity, the maximum point will appear at the first point. And the first point here is x equal to 1. And if you substitute x equal to 1, what do you have? You have f of 1 equal to e. So, meaning, this quantity, e to the power 1 over n, always less than equal to e to the power 1. That's it. This is the idea how to prove this inequality. So, I forget about this now for the time being, and I continue my solution. Now, the question is, what can we say about the series this? N equal to 1 up to infinity e over n cubed. This is convergent. Why it is convergent? I say it orally here. This is constant multiple of a p series. 1. Constant multiple of p series with p equal to 3. And 3 is greater than 1. Okay? So it is convergent. P series with E multiple, so that's also convergent. A constant multiple of a convergent series is convergent. So yes, you're supposed to agree now that this is convergent. I leave the justification for you. It is constant multiple of a P series with P equal to 3 and 3 is greater than 1. Okay, fine. If this is convergent, what can you say about the series here? Then the series with absolute value n equal to 1 up to infinity, absolute value of minus 1 to the n e to the power 1 over n cubed is what? Convergent. Why this is convergent? I will say by comparison test. Okay? By comparison test, this is what we have. This is convergent by comparison test. Fine. If it is convergent by comparison test, what can you say about the series without absolute value? That series is convergent absolutely. It is absolutely convergent. So it is convergent. So what is the conclusion now? This gives what? This implies now. This implies our series here, which is n equal to 1 up to infinity minus 1 to the n e to the power 1 over n all over n cubed is absolutely, if you like, convergent. And since it is absolutely convergent, automatically it will be what? It will be convergent. Do we need to check if it is conditional convergence? The answer is no. Since it is absolutely convergent, for sure it is not conditionally convergent, because by definition, in order to be conditionally convergent, it needs to be convergent, but not absolutely convergent. It is absolutely divergent. And this is the end of the solution, and this is the meaning of convergent, absolutely convergent, conditionally convergence, and so on. So what is next? Now we will introduce 2 more tests that will help us to investigate convergence, absolutely convergence of a given series. Of course, once you talk about absolute convergence, implicitly you have the convergence. Okay. Now we have a very interesting test. It's called the ratio test. Of course, it is called the ratio because it involves of 2 things here. Okay, what is the ratio test? It says if you are given a series, any series given, n equal to 1 up to infinity an, evaluate the limit as n goes to infinity of an plus 1 over an with absolute value. Assume this is equal to L. Assume you end up with a number which is equal to L. Then, the conclusion. If this number L is less than 1, for sure this series is absolutely convergent. If it is greater than 1, the test says, or infinity of course, then the series is divergent. If it happens to be equal to 1, then we have no conclusion. The test is inconclusive. Okay? When do we need to use the ratio test? When it is recommended to use the ratio test, and how to use it. To use the ratio test, it is recommended whenever you have powers of n, you have factorials, you have infinite products, something like this. It is recommended to use the ratio test. It is very powerful test actually. We need it a lot when we talk about power series later. Okay. An example of this says test the given series for convergence, and we have two of them. We have one of them that involves like powers of n, we have exponential functions, and the other one involving power of n and factorials. We said in these cases, the first thing that come in mind is the ratio test. Okay, let's apply the ratio test. Once you talk about limit as n goes to infinity of absolute value of an, absolute value will take care of the minus sign actually. So what is left? Let me just write it for the time being, and then it's minus 1 to the power n plus 1. This is n plus 1 to the power 3 all over 3 to the power n plus 1. It's supposed to be divided by an. So it's multiplied by the reciprocal of this. That is 3 to the n all over what? Minus 1 to the n, if you like, n cubed. Okay, we are considering this with absolute value. You can see now the absolute value will take care of these minuses here. Okay, they will be gone, and everything else are positive, so we don't need absolute value. The only thing we need to compute is this. What is the limit? As n goes to infinity, forget about the minuses because of the absolute value. I have here n plus 1 all cubed multiplied by 3 to the n divided by what? N cubed multiplied by 3 to the n plus 1. I need to do some simplification here. You have 3 to the n plus 1 is 3 to the n times 3. That's 3 to the n plus 1. 3 to the n will cancel with the 3 to the n upstairs. So what do we have is the limit. As n goes to infinity, I will now simplify these two, and 3 will survive here. So what do we have? We have the following. We have 1 over 3, that's 1 over 3 times, now combining these two together, so we have n plus 1 all over n to the power 3. Okay? Now look carefully for this expression here. As n goes to infinity, of course this is a continuous function. I can go inside and evaluate. What is the limit of n plus 1 over n as n goes to infinity? That's equal to 1. So the limit here is 1 to the power 3, which is 1. So the final answer is equal to 1 over 3. Now, since this is less than 1, what can you say about the series? The ratio test says, so this series is absolutely convergent. So it is convergent. It is convergent. Absolutely, actually. So this implies the series, the given series is absolutely convergent. The reason of this by the ratio test. Okay? So this is what we have. By the ratio test, it is absolutely convergent. We'll see another example how to apply the ratio test here. We have factorial. We have n to the n. So we cannot apply integral test. I mean, it is difficult to apply the integral test or comparison test or whatever we have done before. But once you come to the ratio test, it will make life easier in these cases. So what should we do? We just evaluate the limit as n goes to infinity, absolute value of an plus 1 over an, but these are positive terms, so it is enough to talk about n plus 1. I am replacing. Okay, let me write one statement before this. It's supposed to be absolute value of an plus 1 divided by an. Okay, I removed the absolute value first because All terms here are non-negative, positive terms we have, so we don't need absolute value actually. What is an plus 1? An plus 1, you are replacing n by n plus 1, so this will be n plus 1. That is also n plus 1 divided by, this is n plus 1 factorial, okay? Multiplied by, actually it's supposed to be divided by an. I take the reciprocal of this, so this is n factorial, and that is n to the power n. Fine. Coming to the factorial, whenever you have n plus 1, okay, n plus 1 factorial, you can always rewrite this as n plus 1 multiplied by n factorial. Okay, by definition of n plus 1 factorial, it is 1 times 2 times n times n plus 1. So we can save n plus 1 and the remaining terms will be what? N factorial. Okay, simplifying here, that will give you limit as n goes to infinity. Okay, I will replace now n plus 1 factorial by n factorial times n plus 1. So we have n plus 1 to the power n plus 1 all over. This is n plus 1 times n factorial multiplied by n factorial divided by n to the power n. Look, n factorial cancels with n factorial. One of these n plus 1's powers will cancel with n plus 1. So what is remaining is limit as n goes to infinity of what? It is n plus 1 divided by n all to the power n. Okay, fine. What is this? You can see now this is equal to the limit as n goes to infinity, and this is 1 plus 1 over n to the power n, and this is something you know from calculus 1, the definition of e as a limit, because this is one of the L'Hopital's rule we have, indeterminate forms we have. As n goes to infinity, this is 1 to the infinity. So you need to use the technique we did for calculus 1 to find the answer, or you should remember that this is the basic definition of e as a limit, and it is just e. And you know that e is greater than 1. Since greater than 1, what can you say about the series? The series for sure is divergent. So the series is divergent by the ratio test. Okay, it is divergent by the ratio test. Now, I have one more exercise that is very interesting in the sense that it will combine the comparison test with the ratio test. Sometimes you need to use different tests to reach the answer. I'll give you the idea of the next exercise here. And the next exercise is call it part C. And part C here we have the following. Okay, we have summation. We have n equal to 1 up to infinity. We have cosine of, okay, n by over 3, something like this, all over n factorial. Is it convergent, conditionally convergent, or divergent? That's the question. Investigate the convergence of the series. Test the series for convergence. All these are equivalent. Okay. So, is it convergent? Is it absolutely convergent? Is it conditionally convergent? You know we have cosine something here, so it's sometimes positive, sometimes negative. We cannot apply comparison test directly. So what I will do, I take the absolute value. Once I take the absolute value, I have cosine of n by over 3 over n factorial. I know that this is always less than what? Let us say less than or equal to, this is less than 1 over n factorial. Okay? And we know that this is greater than or equal to 0, for sure. So we make a simple trick here to insert the comparison test. Now, we will investigate the convergence of this series. If it happened to be convergent, then by comparison test, this series is convergent. The series of this term, I mean, is convergent with absolute value. And if it is convergent, it means the original one is absolutely convergent. That's the idea of the solution. So the first step, step number 1, look for this series. Step number 1, let's organize our work here. Step number 1, we study this. We study this series, which is n equal to 1 up to infinity 1 over n factorial. Okay, how to study this one? We have factorial. So the ratio test may be helpful here. So I will use the ratio test. Using the ratio test, what do we have is this. The limit as n goes to infinity, and that is 1 over n plus 1 factorial, okay, divided by 1 over n factorial. So it will be n factorial divided by n plus 1 factorial, and you can show that this is limit as n goes to infinity 1 over n plus 1, and this is equal to 0, which is less than 1. So what is the conclusion? The conclusion, this series is absolutely convergent. This series is absolutely convergent. This implies this series 1 over n factorial, n equal to 1 up to infinity is, I would say, AC for absolute convergent. Okay? Absolutely convergent by the ratio test. Fine. If it is absolutely convergent by the ratio test, for sure it is convergent. If it is convergent by comparison test, this one is convergent. Okay, I will write this statement for you that so we have this implies now, this implies this series which is n equal to 1 up to infinity with absolute value, and that is what? That is cosine n by over 3 divided by n factorial is convergent. By what? Convergent by comparison test. Fine. If it is convergent by comparison test, what can we say about the series without absolute value? This implies the series we have n equal to 1 up to infinity cosine of n by over 3 all over n factorial is convergent absolutely. Why it is convergent absolutely? Because the series with absolute values is convergent, so it is convergent absolutely. That is what we call the ratio test, and how to apply it directly and how to link it with another test to investigate convergence. We will have one more test, is called the root test, and that will be our next point. Now another test of interest is called the root test. The root test says if you are given an infinite series, n equal to 1 to infinity, okay, summation of this, and assume that you have the limit as n goes to infinity of the nth root of the absolute value of an is equal to L, then you have three cases again. If this L is less than 1, the series is absolutely convergent. If it is greater than 1 or infinity, divergent. If L is equal to 1, we have no conclusion. To see how to apply this test, of course, this test is recommended whenever you have the exponent is involving expressions of n. So the root test, or what we call sometimes, the nth root test is recommended here. So the root test here says if the limit of this is equal to L and L is less than 1, it is absolutely greater than 1, divergent, equal to 1 is inconclusive. Let us see which one of them will be gained here. So what should I do? I have positive terms, so I don't need the absolute value here. I directly evaluate the limit as n goes to infinity, the nth root of an, or absolute value of an. This will give me the following. The limit as n goes to infinity, the nth root of an, if you take the nth root of the exponent here, so that is the nth root of whatever we have here, 3, okay, this is 2n, sorry, plus 3 divided by 3n plus 2 all to the power n, and clearly now this is equal to the limit as n goes to infinity, and that is like 2n plus 3 divided by 3n plus 2. If you divide by n in the numerator and denominator, this is what you have here, limit as n goes to infinity. Divide by n, this will be 2 plus 3 over n divided by 3 plus 2 over n, and as n goes to infinity, clearly this goes to 0, this goes to 0, so the final answer is 2 over 3, which is less than 1. What is the conclusion? Since the limit is 2 over 3, which is less than 1, so the given series is absolutely convergent. And since it is absolutely convergent, for sure it is convergent. Okay, we have one more interesting case. That is what happened if the limit is equal to 1. If the limit is equal to 1, these two tests are not helpful. So what do you need to do? We need to investigate using other tests. For example, the alternating series test, geometric series test, etc. We have different tests now for investigating convergence of series. And we know how to move from one to another. Sometimes we need to make the use of more than one. For example, the previous examples we did, we have to use the comparison test together with the ratio test. Sometimes we need to use comparison test with other tests, and etc. Okay, let me summarize what we have done in series to conclude this discussion of series convergence or convergence of series. We started this discussion of series by introducing the meaning of convergence of series, and we said it is the construction of the sequence of partial sum. If the sequence of partial sum is convergent, we say the infinite series is convergent. Then we went to the geometric series, a specific type of series. We have a test called geometric series test. Then we moved to the telescoping series, where in these two series we were able to calculate exactly the sum. Okay, sorry for this. Then we have the nth root test of divergence that says if the limit of the nth root is not equal to 0 or does not exist, the series is divergent. Then we move to another part of or another test which is called integral test. And in the integral test we have some criteria. We have a series where we can define a function that agrees with the series at the integers. That function should be continuous, decreasing, etc. We have 3 conditions need to be checked, and then we take a link between the integral, the improper integral, and the convergence of series. We move later to define what we call comparison test and limit comparison test. Then we have a specific type of series called alternating series, and we have what we call alternating series test. Okay? So we have also 2 conditions to be checked in order to say the series is convergent. And finally, we introduce the meaning of absolute convergence, we introduce the ratio test, we introduced the root test. This is basically a summary of investigation of convergence of series. That's it.